Okay, here in example 2, we're going to find the area of the region bounded by x equals the sine of y and x equals y squared minus 1. Draw myself a quick sketch of these two curves. X equals the sine of y. It's kind of like that. Of course, it continues in both directions. And x equals y squared minus 1. It's going to be a parabola that goes this way. And so the region we're finding the area of is this region right in here. And now I need those intersection points in order to find the region, the y coordinates of those intersection points. And I could, again, set these two curves equal to one another and find the intersection point that way. Or I can use my graphing calculator to help me. If I'm going to do that, I'm going to graph the inverses of these. And that's what I'm going to do. I'm going to take my graphing calculator and go ahead and graph x equals the y equals sine of x and y equals x squared minus 1. And I get a picture of the inverse of these two curves. You see what the region looks like, very similar to the one that we have graphed there. And when I find the intersection points on these, they're going to be the inverse of the actual real-world intersection points. So I'll go ahead and calculate the intersection. The first intersection point is negative 0.6367 and negative 0.5945715. And so I want to switch those coordinates in the real world. And so the x coordinate is the y coordinate and the y coordinate is the x coordinate. Since I want the y coordinates of the intersection points in reality, I'm going to use the x coordinate from this graph. And so my lower limit of integration is going to be negative 0.636, etc. So that negative 0.636. 7327 as my lower limit of integration. And I'm going to find the other intersection point for the other limit of integration. And scroll over here to the outside of that so that it picks up the right intersection point. And so the x coordinate of that intersection point is 1.40964. So that's the y coordinate of the real intersection point. So 1.40964. And my upper curve in the inverse graph is the sine of x. So in reality, and you can see from the picture, the curve to the right of the bounded region is the x equals sine of y. So that's going to come first in my integrand. So I've got sine of y minus y squared minus 1. And I'm going to integrate that with respect to y. I'm going to go ahead and do that on my calculator as well. Pull my calculator over here where you can see it. So I go out to my main screen and pull up my numerical integral and switch the variables on here. Oh, I missed a negative sign. Insert that in there. And 1 point. And we go ahead and integrate it, and we end up with the area of the region. So 1.670 is going to be the area of this region. And that's the end of example 2.